This is Mrs. O'Neill for AP Chemistry, Chapter 13, Section 5, Colligative Properties. In this section, you're going to observe that some physical properties of solutions depend on the identity of the solute. You're going to apply that knowledge of colligative properties and how a solute lowers the vapor pressure, increases the boiling point, and decreases the freezing point of the solvent that it's in. And we're going to understand osmotic pressure. So cooking instructions often call for the addition of a small amount of salt to cooking water. Dissolved salt elevates the boiling point of water. And I don't like them saying that. I like to say dissolved salt elevates the boiling point of the solution, the salt water solution. You will learn how to calculate the amount the boiling point of the cooking water rises. So the three colligative properties are boiling point elevation, freezing point depression, and this osmotic pressure. So have you ever wondered why we actually do add antifreeze to our cars? Well, because it lowers the freezing point of the solution, so it helps keep our cars being able to drive in the cold weather, and it also helps elevate the boiling point. So in other words, we can drive it on a hot summer day. So what happens when you add that salt to boiling water right before you're adding that pasta? Well, there's a lot more bubbles, right? All of a sudden it kind of bursts into bubbles. Well, why does that happen? Well, we take that 100 degrees Celsius H2O, and now we've made it 102 degrees Celsius of salt water, which of course helps us cook that pasta quicker. So colligative properties. Again, pause, fill in the blanks, and then play to hear my words. Colligative just means collection, okay? So colligative properties are going to depend on the number of particles or that concentration. And the presence of these solutes are going to affect the boiling point and the freezing point of the solvent. But again, I like to say now it's the solution, right? The solution has changed its freezing and boiling point. And this is also going to help us to determine the molar mass of substances. So remember we talked about vapor pressure before. And remember we talked about how, okay, we have water, we capped our flask, how much vapor pressure is going to be those H2O molecules. Well, now let's add some salt water in here and cap off our flask. Well, what happens to our vapor pressure of that solution? Now, it says here a non-volatile solvent lowers the vapor pressure of solution. Remember, volatile is something that's going to go from a liquid to a gas very quickly. So a non-volatile solvent really just means like salt. Your salt is non-volatile. Your salt does not go from a liquid to a gas very easily. Okay, so the molecules of the solvent must overcome the force of both the other solvent molecules and the solute molecule. So let's look at this in a little bit more detail. So we have pure H2O, let's say as an example, and so we have H2O molecules and we have all of this vapor pressure up here because of all these H2O molecules. Now let's take something like salt water. Okay, so now this solution contains a non-volatile solute. So let's say salt water. So remember that salt is going to dissolve into Na plus and Cl minus. Well, what happens to that Na plus and Cl minus? It gets hydrated with those water molecules. Well, if it's hydrated with those molecules and it has more of an attraction with those water molecules, less water molecules are going to cause vapor pressure. So hopefully that makes sense. It's going to lower the vapor pressure of that solution when we add salt to our water. So here we go. In a pure solvent, equilibrium is established between the liquid and the vapor. And here we have in a solution, those solute particles reduce the number of free solvent particles to escape from that liquid. So we have less vapor pressure. So we take something like this in a closed container. Okay, everything is closed. We have an aqueous solution like salt water, and we have pure water. So remember that pure water is going to have a higher vapor pressure. So as we let things evaporate or do its thing, more pure water molecules are going to evaporate than the water molecules coming from the aqueous solution. So eventually, this is what should happen. Water is going to condense faster into the solution because of those IMF attractions, right? Those ion dipole attractions. So Raoult came up with his law, and it's very similar to the one that you'll see on your reference sheet. The pressure of the solution equals the pressure of the solvent times that mole fraction. And we've used this in the gas law problems. So we're going to use it again, slightly different though. So see if you can come up with an answer here and, of course, the explanation. Hopefully that makes sense to you. So let's look at this practice problem, and I'm not going to have you pause and do it on your own this time because this one is tricky. So I'm just going to kind of walk you through it step by step. So the first thing to think about is what should happen and why. Well, the pressure of the solution should decrease because we're adding those particles, so it's going to lower that vapor pressure. And mathematically, we are going to multiply by a mole fraction, so which means we're going to be multiplying by a decimal, so it should also decrease. So let's look and use this formula. So we plug and chug. We need this x, right? We need that mole fraction. Well, that mole fraction is going to be tricky. For some of you, you're like, we're going to find the moles of the water and the moles of the copper 2 chloride. Yes. Here, though, again, a little tricky because we're going to use that density. So milliliters to grams using density and then using the molar mass to get to moles. And here we have moles of copper 2 chloride, which most of you think, oh, yeah, that's not a big deal. We're going to use molar mass. However, copper 2 chloride is a strong electrolyte. It's going to break apart into 3 ions, 1 copper ion and 2 chloride ions. So we have to take that into consideration. So the amount of moles is not this 0.393. The amount of moles is 1.179. We have to take into consideration that it's going to break up into ions, and those ions are the particles that are going to be in our solution. So now we can use those numbers. We can plug and chug, and we get that as our x. So back to the original equation, plug and chug. 99.4 torrs. However, it says, what is the change in the vapor pressure? So we have the pressure that they give us of the pure water. They give us the pressure of the solution that we found out using the equation. But what we're going to do to those two numbers is subtract, because we want to know what happened to the change. How much did it change? It changed 2.7 torrs from the normal pure water to the solution of the water with the copper chloride. So that's a pretty big difference in pressure. So boiling point elevation, again, it's going to lower the vapor pressure of that solvent, meaning that it's going to raise the boiling point. So that's why it's called boiling point elevation. It elevates that boiling point. And notice this equation. It is not on your reference sheet. You do not need to know how to use it for the AP exam, but I am going to show you some example problems that you might do in college one day. But there's going to be a trick to this in a moment. So read over this, see if you can get the answer. Hopefully that makes sense. The wood frog is a remarkable creature because it can survive being frozen. Scientists believe that substance in the cells of this frog acts as a natural antifreeze, which prevents the cells from freezing. Although fluids surrounding the frog cells may freeze, the cells themselves do not. So in this section, you will discover how a solute can change the freezing point of a solution. So that's where we get freezing point depression. So the solute lowers that vapor pressure of the solution, lowering the freezing point. So that's why it's called freezing point depression. It's depressing that freezing point. So again, you have a very similar equation, and we're going to take note of that again in a moment. Also, there's these Malal constants. The Kb and Kf of water are these values, and again, you will see them or they will be given to you if you need to use them. So this is a nice graph representation. So we have pure water, which are only dipole-dipole, or it's a polar molecule, IMFs. Here we have vapor pressure of the solution. Well, what happens? That vapor pressure lowered because now we have that ion dipole IMFs, right? So pure H2O, but now we have more attractions of that water to those ions, so it's going to lower the vapor pressure. So let's look at here. Here's our freezing and boiling points of the normal solvent of water, but if we add some salt to our solution now, we have now depressed our freezing point and elevated our boiling point. Okay, so that's where that change in temperature for F and B come into. So pause the video, read, look at the graph, and see if you come up with the correct answers. Hopefully you did. So can you read this question, answer it, and the why? Hopefully you got that because we talked about breaking up into more particles. The KCl will break up into 2 particles and the CaBr2 will break up into 3 particles. So electrolytes in solution are going to depend on the number of molecules. Remember, an ionic compound should have a bigger effect than a covalent compound because it breaks apart. It dissociates into ions. So that example, NaCl, we've said many times, will make 2 moles of ions. But how about something like aluminum nitrate? Well, that's going to make 4 moles of ions because it breaks into 1 aluminum and 3 nitrate ions, making 4 moles of ions. So electrolytes have a bigger impact on melting and freezing points per mole because they make more pieces. So that should make sense. So this von Hoff factor is this I, and this I tells us that the moles of particles in a solution divided by the moles of the solute dissolved is going to impact our change in temperature. So how much or what is our value here of I if we have a formula like NaCl? Well, it breaks into 2 ions, Na and Cl, 1 of each. How about B and C? Can you pause the video and see if you get the correct answers? Again, we're breaking up into 2 K plus 1s and 1 SO4 negative 2. And letter C, ooh, lots of particles there, right? 3 irons and 2 phosphates. So the value of I is usually less, right? The actual value of I is usually less because of what's called ion pairing. And remember I said, when we crystallize our salt solution, we still can taste our salt, right? Why can we taste our salt? Because some of that Na and Cl are going to come together and make that compound. So ion pairing actually increases with concentration, but the I then, this I value, is going to decrease with increasing concentration, right? So the more NaCl we put into our salt water, right, the more Na and Cl ions we have, but then of course there's going to be more ion pairing, right? And that makes sense, and that's what happens with our supersaturated solution. So if you look at our equation now we're going to add that I. So the following problems, I'm really just kind of click through. They're not going to be on the exam, but you might see them again in college chemistry. At least that's what students have told me in the past. So I wanted to at least give you some examples. So you might want to star these or whatever that says, don't worry about studying them. We're not going to do practice problems, but I want you to have some examples in your notes so you can refer back to them later on. So here's example 1, and I'm just going to click through the solution process. And I am more than willing to answer any questions on these, but again, I don't want you to spend too much time on these because they're not necessarily going to be on the AP exam. However, you might see them again in college. Okay? And we want to remember that we are actually subtracting here because the normal would be 0, and we have to subtract the 5.99 because that's going to be the actual new change, or the new, I should say, the new value. Example 2. So here I really wanted to show you with or without that I in the equation. So we have 103.07 and 101.54. So again, somewhere in between, remember, because of that ion pairing. So this is the value with the I, this is with it without. They are close, and again, that true value would be somewhere in between because of that ion pairing. So neither value is going to be 100%. Example 3. This is in the beginning, that molar mass of a substance. It helps us determine that. And we have 13 grams per mole. And if they would give you a list of, excuse me, if they would give you a list of possible compounds, you'd be able to identify it by the molar mass. Example 4. Okay. There you go, okay? Or you can also do it the dimensional analysis way. And osmosis is just the movement of solvent